we're gonna get started. Couple things first, as it came up in the chat. Next week is CASP testing, 4th through the 7th. I don't know if there's any juniors in here right now, but juniors have to take the CASP. If you haven't taken the CASP and you're a senior, they might pull you to take it if you missed it last year. That's always something that happens. If you don't know, the CASP is essentially your first opportunity to show that you are college ready in English and math. That's about it. If you do not do well on it, you have other opportunities to show that you are college ready. It is just your first opportunity. Standardized test, we take it through the computers. It's not a lot of fun. But that will be next week for all juniors, which means classes will not start until like 12:30, I think. Yeah, I should probably put the start time. I have the fact that CASP testing is happening on our calendar in the course. I do not have what time classes start, though. I'll add that later today. But I believe it's like 12:30. Or somewhere close to that. Each class will only be 45 minutes long, give or take, right? So it's going to be really fast on all those days next week. It's not a lot of time in class. But yeah, so be aware of that. 8:30 to 12 is CASP testing. So if you're not taking the CASP, you don't have to be here that early. All right, so just a quick reminder about that. Other than that, I hope everyone had a great weekend. I hope you guys are doing all right, feeling all right. We're heading to that home stretch. Got about 6-7 weeks left in the semester. All right, so it's just gotta make it through those last few weeks. That's about, just kind of push it, get stuff done, do what you got to do, and get through the last little bit here, and then we'll all leave this crazy, somewhat just nonsensical year behind us and try to move forward. All right. So as far as today goes, I want to take today to kind of wrap up chapter 10, go over a couple of things specifically that I haven't, I felt like I haven't spent enough time on. I want to make sure you guys are aware of. So we'll do a little bit of notes. I'm just going to use one note to kind of go through these things and make a couple of points. And that'll be like it. I've got the, I'll get to that afterwards. Never mind. All right, so let's make sure I can actually make this stuff work. So I will share my screen. Maybe. That's screen 2. All right. Excellent. So I believe everyone can see my screen now. Those in the classroom, you can look at it on the projector. Those at home, please look at the shared screen. And we're going to start running through this stuff. Okay, so chapter 10, again, was about comparing two populations or two groups. Right? And typically we're looking at differences when we're comparing the two things. We're trying to determine if there is a difference. Is the difference significant? What is the difference? All right. Those are the kind of things that we're looking at. So starting with section 10.1, comparing two proportions, we started with sampling distribution. Right, what's the sampling distribution of the difference of the two proportions? Right, and when doing that, we should always be checking our conditions. Right, I think I'm going to make that a little bit thicker of a pen. Make this look better. That's easier to see. All right, so we have our conditions that we check when doing a sampling distribution. First, we want to check the large counts condition. All right, and remember that's just making sure that you have at least 10 successes and at least 10 failures from each sample. And that goes for both samples from both populations. Got to be at least 10. And then we check the 10% condition, When doing the sampling distribution, the 10% condition lets us know that we can actually find a standard deviation that is reasonable. If the 10% condition is not met, then things kind of go crazy. And we don't want things to go crazy. Right. Then, right, once we check our conditions, large counts 10%, we can then do calculations. We can determine the mean of the sampling distribution. And our mean will be notated with mu of p hat 1 minus p hat 2 is just equal to p1 minus p2. Right, so again, p1, p2, those are the population proportions. All right, from the true population proportions, which when we're doing a sampling distribution, there's an assumption that we know what those are, and those are provided so we can use them. Later on in confidence intervals and significance tests, we do not know what those are, and we're trying to estimate them. So we have our mean, and we can also calculate our standard deviation. Which is sigma p hat 1 minus p hat 2. And that is equal to this crazy square root. I'll leave the top off of it right now so I can write this. We've got p1, 1 minus p1 divided by n1 plus p2, 1 minus p2 over n2. Right, and again, p1 and p2 are the true population proportions. N1 and N2 are the sample sizes of the two samples from each proportion. They may or may not be the same. That's why they're labeled differently. All right. And so then these are the things we can find out when doing a sampling distribution. We can get the mean of the sampling distribution, standard deviation of the sampling distribution. Right. We could then use these things to standardize a certain proportion, see what's the probability of getting a proportion greater than or less than that by using the normal kind of standardization things where we get our proportion value minus the mean divided by the standard deviation, or in this case, the standard error there, standard deviation, right? We can standardize, we can do proportions, we use table A. Right? We can do all that using the mean and standard deviation we found here. Okay, so that's sampling distributions. Next, we move on to our confidence intervals. And I do apologize. This is going to go relatively fast. I'm not meaning to do examples of this stuff again right now. I'm just trying to run through the things that we're using and kind of the ideas. All right, so once again, when we do confidence intervals, we have to check conditions. That always comes first. And in this one, we add randomness as a condition. We still have our 10% condition. And this is when sampling without replacement. And our large counts condition, which again, the 10% and large counts are the same as they were previously for sampling distribution. We have to make sure that our sample size is of the population size. Large counts, we have to have at least 10 successes and 10 failures from our sample. And random, either we can have an SRS, randomly selected sample of people or individuals or whoever we're interested in, or we can look at this as an experiment possibly where we would have random assignment. We just need to have randomness. Right? We check our conditions, those conditions are met. Right? And we will use the 2 sample Z interval for the difference of 2 proportions. This is our inference method that allows us to estimate the difference. Okay. And this formula, I'm going to scroll up. We have p hat 1 minus p hat 2 plus or minus z star times square root p hat 1 times 1 minus p hat 1 over n1 plus p hat 2, 1 minus p hat 2 over n2. That whole thing is in that square root. This calculation allows us to find the confidence interval. We get a larger value and a smaller value. Once again, z star is our critical value. And we find this by using table A and the given confidence interval that we're looking for, the confidence value, like 95%, right? Gives us 5% left over in each tail, gives us 2.5% for one tail. We'd go and find, you know, that proportion in table A on the interior, which would be 0.025, right? Find that. That corresponds to a z value. We then use that z value, the positive value of the z value for z star. Right? So we have that. Then, again, this part, the square root part, that section there is referred to as the standard error. It is no longer, it's similar to the standard deviation, but because we're estimating and we're using the sample proportions, that is the standard error now. So if you ask for standard error, it's that square root thing. Right. Is there any questions so far? Okay. So that then leads us to our significance tests for the difference of proportions. Does anyone need a little more time to write anything down before I scroll up? Right there. All right, then significance tests. Again, we have our conditions we must always check. We must show that we have checked them. Okay. We need check for randomness, 10% again, when sampling without replacement, and large counts. Okay. And then when these conditions, or if these conditions are met, we will use the 2 sample Z test for P1 minus P2. And again, that is our inference method. This allows us to make an estimate based on the provided data. Okay, and this allows us, we are testing the null hypothesis that P1 minus P2 is 0 against some alternative. Right, the alternative would depend on the context. And we will calculate the Z statistic, which we just use Z, and that equals some of this craziness. So we get p hat 1 minus p hat 2 minus 0. The 0 comes from the hypothesis. If we were to hypothesize the null hypothesis that the difference was some value, then that value would go in as minus that number. But typically we're just going to be using 0 as no difference. And then we use this massive square root again. We do p hat c, and I'll explain what c is in just a moment, minus 1 p hat c over and 1 plus p hat c, 1 minus p hat c, all over n2. That's all in the denominator. Okay, now p hat c. So something that comes up in the practice problems that I have, but it is not, we haven't seen an example necessarily in class, but this is used when conducting a significance test, and we are assuming that that P1 minus P2 is 0, or that P1 equals P2, right? And we get P hat C, right, which is the count of successes in both samples the size of the two samples combined. And then that is used in calculating the standard error, that's that big square root. This only is used during significance tests when assuming P1 equals P2 in the null hypothesis. Okay. So this is very specific to significance tests with proportions. We have this extra kind of little variable to calculate. Okay, and this is called a pooled sample proportion, or combined sample proportion, hence the little c. Is there anything I can clarify here? Anything I can explain for this? This is section 10.1 in a nutshell. These are the three main things that we're doing in section 10.1 with proportions. All right, and does anyone need a moment to write anything down? So then we'll move to 10.2, which is comparing two means. And again, we started with sampling distributions. Again, we have conditions. Right now, with our sampling distributions, with proportions, the large counts condition, right, making sure there's at least 10 successes and 10 failures, is checking for normality. As long as that happens, we can kind of assume normality, that we'll have an approximately normal distribution. For means, right, we have that normal large sample condition that we check for confidence intervals and significance tests. But in chapter 7, and in this case, it's not necessarily referred to that way. We check the central limit theorem. It's essentially the same thing. We're making sure that the sample size is at least 30, right? And as long as the sample size is at least 30, we can assume normality for the distribution. If the parent population was normal, we can assume normality for the sampling distribution, right? And so it's essentially the same idea, normal large sample. Right? So again, we check our normal large sample condition. Right, worst case scenario, if those two things don't happen, then we have to graph our data and check to see if it's normal, which hopefully we don't have to do. Right, we have also referred to this condition as the central limit theorem. And then, as per usual, we have our 10% condition. Once we've checked our conditions, we can calculate the mean. So we have mu x bar 1 minus x bar 2 is just equal to mu 1 minus mu 2. If that wants to catch up, there you go. All right, and again, mu 1 and mu 2 are just the true means from the populations, which when we're doing sampling distributions, we should have. And then we can also check for standard deviation. We have sigma x bar 1 minus x bar 2 is equal to the square root of sigma squared 2 over n, I'm sorry, that both be a 1, 1, plus the variance, right, of sample 2, and that all goes under our square root there. And that is our standard deviation. Once again, we could standardize these scores and then use table A to find proportions or probabilities of getting a certain mean less than some value or greater than some value within our sampling distribution. And then, where's my mouse? There it is. We also have confidence intervals again. And again, check our conditions. Okay, random, 10%, and normal large sample. Once conditions are met, right, if they are, then we will use the 2 sample t interval for mu1 minus mu2. And that will be found by taking the difference between our sample means, x bar 1 minus x bar 2, plus or minus t star, our critical value, times the standard error, s squared 1 over n1 plus s squared 2 over n2, where s squared 1 and s squared 2 are the variances of the samples from population 1 and population 2. And of course, n1 and n2 are the sample sizes. Similar to what we saw in proportions, t star is our critical value. And that comes from table B, based on the confidence percentage, the confidence interval that we're looking for. All right, recall on table B, the bottom row of table B shows percentages or confidence intervals. We find that confidence interval, check our degrees of freedom, which I'll address here in a moment, and find the corresponding t value that goes along with that. That becomes our critical value. And again, this section here is referred to as our standard error. And last little tidbit here. Right, the degree of freedom is equal to whichever value is less between n1 minus 1 and n2 minus 1. Whichever one's smaller. That's the degree of freedom we use for the whole thing. I don't find two different t values. I don't use two different degrees of freedom. Whichever one's smaller, I use. Okay. Lastly, we'll do our significance tests. Once again, check your conditions. All right, we need random, we need 10%, and we need the normal / large sample. All right, same conditions. When those conditions are met, we will use a 2-sample t test. For mu1 minus mu2, for the difference of the population means. Right, and in this case, we use the t statistic. Which we just write as t. We have x bar 1 minus x bar 2 minus mu1 minus mu2 divided by square root s squared 1 over n1 plus s squared 2 over n2. Right, and this is testing the null hypothesis that mu1 minus mu2 is some value. It could be some hypothesized value. We might actually have a difference we're looking for or no difference. So you can say 0 or some hypothesized value. There are cases where we might have a value for that difference. Again, we will use table B. Right, once we have our t statistic, I cannot write today. With degrees of freedom equaling the lower of n1 minus 1 and n2 minus 1. All right. So again, this is the rundown of the 3 major things that we're using in chapter 10 when comparing to population or group means, finding the difference, estimating the difference. Also keep in mind, we should be using that 4-step process like all the time now. If you're asked to find a confidence interval, calculate and interpret, right? Test the significance, 4 steps, right? State, plan, do, conclude. Those things should be done. So similarly, like we had the special case when doing a significance test with proportions, right, where we use that pooled proportion. There's a consideration that we have to have when dealing with means, and that is the last little thing we'll cover here. When do we use matched pairs which is what is essentially still using chapter 9, right? In which case we find the difference between our matched pairs, and then that is the value we use. We have a single one sample at that point, and it goes back to chapter 9, right? Or do we use a two sample T procedure? Right, so we have a few different scenarios that we're going to look at here and decide which one should we use, matched pairs or two sample. All right. So our first scenario here, to test the wear characteristics of two tire brands, A and B, each brand of tire is randomly assigned to 50 cars of the same make and model. All right. Will this be matched pairs or will this be two sample T procedures? All right. And the basic consideration you have to ask is, will there be, am I collecting two sets of data on a single like individual or a single set of individuals, or do I have two completely different sets of data for two different like groups of people? It's kind of the consideration you're trying to make. In this case, right, this will use two sample, right, chapter 10. Right, because I'm going to get two separate sets of data. I basically have two groups, and they're each getting randomly assigned a treatment, tire A or tire B. Right, since I have two separate groups getting the treatments, this becomes a two sample procedure. Right, the second example here, to test the effect of background music on productivity. Factory workers are observed. For 1 month, each subject works without music. For another month, the subject works while listening to music. The month in which each subject listens to music is determined by a coin toss. Right? We're collecting data on one individual 2 times in this case. Right? This is a matched pairs T procedure. Right? I have one individual who's getting two different measurements using two different treatments. So in that case, we're going to be comparing the difference for each individual, and that becomes a matched pairs. I'll get one number at the end of the day for each person, the difference between the two results. All right, scenario 3, a study was designed to compare the effectiveness of two weight-reducing diets. 50 obese women who volunteered to participate were randomly assigned into two equal-sized groups. One group was using diet A, the other used diet B. The weight of each woman was measured before the assigned diet and again after 10 weeks on the diet. We have two groups being randomly assigned a treatment. Each group, I receive essentially one data point from each person. This becomes a two sample procedure. Okay. Fourth scenario. To compare the average weight gain of pigs fed two different rations, 9 pairs of pigs were used. Pigs in each pair were littermates. A coin toss was used to decide which pig in each pair got ration A and which got ration B. This one is a little tricky, but this ends up being matched pairs because we have our two pairs and we're collecting the difference in weight gain between the pairs. That difference is the data that we're using. Right? And so that ends up being a matched pairs procedure. Right. Next scenario, separate random samples of male and female college professors are taken. We wish to compare the average salaries of male and female teachers. In this case, we have two separate proportions, male and female. We're collecting data and then comparing them. That will then be a two sample procedure. And our last scenario. To test the effects of a new fertilizer, 100 plots are treated with the new fertilizer, 100 plots are treated with another fertilizer. Computer's random number generator is used to determine which plot gets which fertilizer. Again, we're creating two separate groups, collecting the data and then comparing the data. That will be a two-sample procedure. All right. Are there any questions? Is there anything I can clarify about this context here in the two different scenarios that we end up with? Okay, so that was the rundown that I wanted to do today. I wanted to give you guys kind of just an overall look in chapter 10 between the two sections, the things that we're using. And then the two little things that I wanted to highlight was the matched pairs versus two sample T procedures dealing with means. And right, the pooled sample proportion that is used when doing a significance test. Okay, those are things we didn't necessarily get to see examples of last week. There are some practice problems that use these two things, so you're welcome to look at those. But I wanted to make sure and talk about those and give a quick rundown of everything that we saw in this chapter as far as notation and calculations, inference methods, and all those things. So I'm going to stop sharing my screen. So lastly, like that essentially brings us to the end of chapter 10. I have the multiple choice assessment ready and it should be published as long as I clicked all the right boxes. And I will have the free response questions ready soon. I do not quite have those ready yet, but they should be ready in the next couple days. Tomorrow, what we're going to be doing is stuff having to do with preparing for the AP exam. We're going to be talking about your computers, making sure you have the testing application if you are testing, going through what that process is going to look like and feel like. And we're going to do a little sample, like practice AP test. Obviously, it's for practice. It will not be part of your grade. It's to look and see what the testing environment will look like and feel like, what the timing is like, and all that stuff. So we're going to do that tomorrow. Yeah, that about sums it up for today. So if you do have any questions, comments, concerns, please make sure to let me know. I highly encourage you guys to look at the resources for chapter 10, the practice problems, the solutions, and for all the previous chapters if you have time. Right? There's lots of resources in Canvas. And other than that, I hope you guys have a great rest of your day, and we will see you tomorrow.